recording? Let's see my CPU usage. You're right. Let's see what happens. Okay. I think we're online. You have to wait for the time to come. You see this working like trash. Let's leave this here. Okay, Monster, you're blocking the light. We're about to start. Let's get started. My little boy, I'll be here. We need more light. Let's see. Let's turn this guy on. If it is on. Oh, it's not on. Okay. Let's put it on. We had a little disaster. Let's set up one more light since Abby here is blocking the light. Okay. Oh yeah, it's better. Maybe let's lower it a little bit. Okay. Let's see, let's start. Okay, so what was our syllabus? Our syllabus was I'll try to write it here. So we'll have put it here on the main page. So original syllabus. Right, so we have at least that's the intent, the initial intent. Let's text a friend to see they can join us. Okay. Let's try to get going. So we want to look at a finite different approximation of derivatives for maybe first and second order. I think that makes sense. The boundary value problem also, it makes sense. Maybe initial value problems to solve systems that evolve over time. I think Euler method for linear and nonlinear problems will be interesting. And I don't know if we'll be able to cover all this in this stream, but let's just get started. So let's make first section here of finite differences and to approximate derivatives, and then we're just gonna start looking at the main book that I'm basing these notes on, which I have in physical form somewhere in my library. Where is it? There. Oh, it was a friend from it was a gift from a very good friend. So I'll just put it here. And I have also a PDF here, so we can go here. Let's go to a specific section that we want. I mean, this is obviously the beginning, so we'll go right into it. And this is a great book, by the way. So if you are curious as to how to learn more, this is a good way. All right, so maybe we can start with, I'll start describing what's happening here actually. So we have a function u of x, and we want to compute the discrete derivative. And I think most of us learn the limit definition of a derivative basically using this, and this way they call it an obvious choice to have, okay, the derivative of u to be equivalent to perhaps this difference u of, at the point x plus h minus u of x. But you have to notice that these points are to the right of the original point x, right? So this is calling it d plus, right? So this is motivated by the standard definition of a derivative, and I think that's fine. But you can also define the d minus, right? Like the derivative previously to the point x, where you're computing the slope of the curve, right, by going u of x minus u of x minus h. And I think this is a great drawing because you have h bar here, x bar here, and you have the slope of the difference between of the function u of x and x minus h, and you have x and x plus h. So these three slopes are kind of different, right? You have, this is the d minus slope, this is the d plus slope, and you have the actual perfect slope, the one that touches precisely at the point that is the function that is being called du0. So each of these formulas give a first order accurate approximation of u prime, meaning that the size of the error is roughly proportional to h itself. So this is interesting. So let's try to write that actually here. So another possibility is to use the centered approximation. So I'm going to use that. And you can see my text here. Yeah, maybe I'll increase the size so you can see better. The center approximation, and we're going to use math symbols. Does that work? Yeah. And we have, so d of 0 of u and r of x. I'm going to define it as, the fraction. I might have to accelerate this part because it's kind of slow. So u, and we're going to skip ahead like x plus h, and then minus u of x minus h, and then divided by 2h instead. So you see what's happening. So I'm moving all the way, and this in a way is the average of the two of the two one-sided derivatives. So this is actually 1/2 times d plus of u at the point, x bar, and then plus d minus of u at x bar. Yeah. And so so this approximation, right, so this approximation, you can see that on the drawing actually, right here. This slope is kind of tilted upwards a little bit, this slope is a little bit tilted downward, and the slope that goes in between is actually more similar than the slope at the perfect point, than the derivative at this point. And so the way that we can guarantee that actually is because we can compute that the approximation, this average here, right, the center approximation, is actually more accurate all the way to a second order. Basically, the error is proportional to h squared. So when h is little, h squared is much smaller than h. And so when you keep in mind, when you basically try to discretize a derivative, you can use the one-sided derivative, for example, if you wanted to. These approximations that we saw before, either d plus or d minus. But in general, it's with the same computational steps, right? You have 2 points. You can get a much more accurate derivative if you use this center approximation. So we'll tend, in this course, we'll tend to use this one. And there are a lot of other clever tricks to approximate the derivative, and you can see them in here, in this equation 1.4. For example, this, it's called a d sub 3, but it's also an approximation to the derivative. 1 over 6h, and these coefficients 2, 3, 6, and 1 here. So the trick is that it is not clear as to why this is a good approximation, but it works. And in fact, it works so good that the error is proportional to h cubed, meaning that it's a better approximation when h is very small. So in this book, they go into the theory as to how do you derive these formulas to make them very accurate in a more general way. And they teach you about basically the errors. And if you ever want to go deep into this, you basically need to remember Taylor expansion theorems. And this is an example of what's happening here. So you're expanding u of x plus h, right, in terms of its derivatives. And so when you want to estimate u prime, you can solve, for example, using these estimates here, or doing some combinations of these two things to get higher order derivatives. And I think that is the trick. So for example, when you do the d plus, as you remember, u of x bar plus h minus u of x, this is the right-handed derivative. When you do that, you take this, it's basically this one minus this term right here. And so you just get left over this section, right? Which you can see here when you divide by h. So you can see here that this is a good approximation for u prime, but the error starts to look like h times some constant plus h squared times some other constant and so on. So the order of the error here is h. Now, if you do the center approximation, which was, if you remember, u of x plus h minus u of x minus h, what you're doing is you're taking this one and your equation, and you're subtracting this equation here. And so these two terms cancel, right? These two terms, they add each other. So you get 2h u prime. And if you divide by 2h, you get u prime. And this guy right here, because it's this minus this, they cancel. So you no longer have an h squared term, and all you have left is a term with h cubed. So you can see here that the error in estimating the derivative of u is of order h squared. So this is kind of tricky and very good. And so we're going to add here into our notes that the error of calculating the derivative by using the centered approximation is of order h cube. I'm going to use math notation h cube. And the proof is done by expanding the terms into their Taylor series. So we're not going to do that since these notes are supposed to be kind of cursory, but we can say, I'm going to write here that the error, so error, which is equal to d sub 0 of u at the point x minus u prime at the point x is equal to, and we have here the equation, right? So 1/6 of 1 over h, sorry, h square, and it's proportional to u double prime. I think I can just go prime, right? Prime of x, and then plus an extra error of order h4. So we basically save this. All right. So I actually don't know if this is working. That's showing what's happening. Is it working? Oh, the mathematics are working. Yay! Okay, great. So we're going to close the preview. Yeah. Okay. So this is how we do it. There are many more finite differences that you can do, and we will, when we're discussing actual problems with boundary conditions, we will see that it's not so trivial to do the center approach. So we might have to do some kind of either directional or one-sided derivative, or come up with a strategy like this one, for example, which is a special, which is when we want a one-sided approximation of the derivative that is actually accurate to a higher level. And the way to do it actually is here. So we're going to save this maybe for later. And the proof shows that the Taylor's expansion of this derivative actually shows that this is the error is proportional to h squared, which is better than the original directional derivative, which was of h. So maybe, and we can save this. Of course, we can do the same for the other side, right? This was a one-sided in the sense that it comes from the left, but you can do it to come from the right, and it will still work. So this, I'm anticipating here that at some point we'll try to solve a problem in one dimension that has boundaries. For example, maybe a string, and the string is fixing one point and fixing the other. When you try to compute the derivative on one side, you cannot take points that are outside the domain, right? You have a hard boundary there, so you can only take the derivative from the inside of the region, and that will force you to do this this type of one-sided derivatives. Now, what about second order derivatives? So this is how we compute the derivative of one derivative. What about second order derivatives? Let's add here first order derivatives. So when you're doing second order derivatives, it's a little bit of the same thing, right? If we remember the Taylor expansion, so remember Taylor expansion for a function for u of x, right? So let's well, for u of x. So how does that look like? So it looks like right, so u of x is equal to what is the way of doing it here? So sorry, u of x, plus h is equal to u of x plus h times u prime of x plus h squared divided by 2. So of h squared times u double prime at the point x plus, and then there's another fraction of 1 over, is it 3 factorial? So 3 to 5. Is that right? So 1 over 1, 1 over 2 factorial, 1 over 3 factorial, which is, 6. And then h cube, and then u triple prime of x, etc. Plus dot dot dot. And so this, you can see here that if we use our approximation for u prime that we used before, the d0, and we replace it here with this error term, and we can then kind of recover and approximate for u triple prime. And that's what they do here, right? It's a repetition of, for example, the second derivative of u, maybe it's the one-sided over the other side of u, and you just do the operation kind of twice. So let's write it down. So I'm going to say here we can therefore recover an estimate for u triple prime using the function evaluated at points, x plus h, x minus h, and x. So we'll do the following. So d square of u at the point x, let's say it's d plus d minus of u of x, and if we actually expand that, we obtain, I'm gonna do it one more time. So d square of u of x, just to help with the understanding. So it will be, fraction of 1 over h, right? And then times d minus, right? So d minus of u of x plus h, right? Because this is d plus, minus d sub minus of u of x, yeah? We close up parentheses. And so now we have to replace this value, and I'm going to copy this. By their internal values. So we're going to go 1, and this is frac of u, no, of x plus h minus u of x, right? That's the value of u at d minus, right? So d minus is that minus h, so you get that. divided by h, and then we close the parentheses and we say now minus again, big parentheses, and we have d minus of u of x, which is, this is the standard definition, so u of x minus u of x minus h, and then the divided by h. We close this parentheses and we close the other parentheses. Now we're set. So this approximation of the second derivative, we just call, we're going to call it, d2 of u of x, and it can be proven that when you actually expand it a little bit, let me see. We get that this formula is approximate to the h square, as we can see in this equation right here. And actually comes to be that formula that is up there. So let me write it here. So that we have a d2 of u of x ends up being, you can see 1 over h squared here, times, and this whole, you get u of x minus h one time. Yeah, do you see it? So minus over here, you get minus gives you plus, so u of x minus h, and then the only one of these, you also get minus, so how many u of x's? So we get minus 1 here, and then minus 2, and that's it. So minus 2 u of x's, and then you get u of x plus h one time, so plus is plus u of x plus h. Yeah. And that's it. We close this parentheses, and that's the definition then of the centered, and you can tell that it's a centered derivative of second order. But now notice it uses 3 points, right? So our best evaluation before used 2 points. For the second derivative, we need to use 3 points. So higher order derivatives, you can keep stacking these d pluses and d minuses, and I think that can help. You can also stack a d0, for example, to get higher approximation. I think they all, you can prove the different degrees of accuracy by doing their Taylor expansions. But it is, but we're going to stop here since most of the problems that we will tackle are in 2 dimensions, but you also feel free to do so. So I think this is a good moment to perhaps try to implement, some of these derivatives in code, just to have them for future use. Okay, so that's going to be interesting. So we can create, maybe I'll save this. We'll create a new file, which, what do we need to, we don't know what we need to import, but we're gonna save it as, so we're gonna define, this is all in Python. So this module will be utilities to compute discrete derivatives, and how do we call the first one? We called centered derivative, and you had to give it a function u. Yeah, so we're gonna say, let's add a note here. So u of x is a function of single variable x. And so it's a callable, right? We're gonna say callable a function of a single variable x. And so what do we want to do? We want to say we want to return a function, right? So we're going to define perhaps d0 of u, right? It's going to be equal. Maybe we want to define a lambda. Let's define a lambda function. So d0 u. I'm hesitating whether we want this or it's going to be a lambda function that given a given x, lambda, it will return what? So it should return the u of x plus the center derivative, right? So let's take a look at what that looks like. So it looks like u of x plus h minus u of x minus h divided by 2h. So u of x plus h minus u of x minus h, and then we're going to divide this by 2 times h. And of course, we're noticing that we need this variable h, and of course it makes sense. Our approximation needs to depend on the h itself. And so maybe we need to give it both the function that we want to derive, but also the step of our approximation, right? So we're going to give it here. Now we're going to add that to, oh, this has no name. Let's save this. So we're going to call it so utils.py. Yeah. So we have a callable. Function of a single variable. Then what? And then we also have h, which is discrete step size. Okay. So we're going to return d0u. Yeah. And that's it. Okay, so maybe we should run some examples to test it with. So for example, let's create a new example. We're going to import numpy as np. This is to get maybe vectors. We're going to import also matplotlib.pyplot as plt to get some plots to show what we're trying to do. And what can we try? Maybe we can try a classic one. We're going to call this, what do we call this file? We call it test utils, yeah. And we're going to give it a function. Let's start with the function u. We're going to start perhaps, what's a classic one? Perhaps x squared is a classic one. So let's define lambda x squared. And we're going to try to, we know what the derivative of lambda is, right? So let's say u prime. We know that it's lambda, 2 times x. We know this, but we're going to compute the discrete derivative. And we're going to change the name so this that we're going to call derivative u, and then discrete derivative of u, and we're going to just call our function from utils. So we're going to import it from utils. Oh. Import, what are we going to import? We're going to import center derivative. Okay. We're going to have our function here. True derivative. and then approximate derivative. And this is called centered derivative. I'm going to give u. And what is the step size we're going to use? Maybe we can use a step size. So step size. Let's call it h as we were calling it. So h will be 0.1. So step size. And then we give it to our function. Yeah. And now we have our function discrete derivative that we can call. So maybe we can do some plots to understand. So obviously our function u is a parabola, right? So it will look like this, but the derivative should look like a straight line. So we're going to plot the real derivative versus the approximate derivative on a given set of points. So let's say np dot linspace. I think we have to put start and stop. So let's say it starts from 0 to 1. So this is going to be very uncreative. I'm going to plt the plot. We're going to plot the real one. So derivative of u evaluated in x. And that should give us a vector of all the derivatives and all these points. And sorry, the x-axis is going to be x, and the y-axis is going to be the derivative. And we're going to label this as the true derivative. And then we're going to plot x now and the discrete derivative, and we're going to label this approximation. Yeah, so now we maybe put a legend, and then we plt the show. And now we're ready. We save this, and we can run it. Oh, haha. Okay, so terminal. Yeah, let's try again. Oh, there's an error. Oh, yeah, this is a function. Sorry, so we need to give it the x. That was my mistake. We try again. There we go. So I'm going to show you on the stream the image. So how do I copy this image? I know what I'm going to do. So I'm going to save it. Maybe I should just show you my entire screen. Okay, maybe that's difficult to do right now. Give me 1 second. So I'm going to save it. Okay. Maybe yeah, in this case it's not so difficult because it's a line. So I'll still save it though. So maybe actually I'll choose a different function to make this a more interesting. So let's choose, instead of x squared, this is just so the notes are a little bit more interesting. Let's choose let's choose sine. That way, and then everything should be ready to run anyway, so we can go and run it. Oh, yeah, sorry. And then the derivative of sine we know is cosine. Okay, that's the real derivative. And now we're going to choose a better slim space. So maybe from 0 to 2 pi. Yeah, that's better. And now we can run it. So we can see a full swing of perfect. And okay. So I'm gonna save this. I'm gonna say this is sine example. I'm going to put this guy here on our README. I'll edit this later. So we're gonna put an image. Copyrighted path. Okay. Oh, this did not work. So how do we put a markdown image? I think it's easier. I just forgot. Oh yeah, okay. We have to put here, sorry. So parentheses, I go image. There we go. And actually there's almost no difference between the obtained result discrete and the one that we get. Maybe if we redo this with an h that's a little bit bigger, it will be so we're going to add a little bit of the code that we're using just to show what we are up to on the oh, maybe it's fine. Maybe I'll do the test utils, but I'll choose a step size that's a little bit bigger. Maybe so that we can see a little bit more error, maybe 0.5. And let's put that picture instead. Yeah, there we go. A little bit of error. I'm gonna put it on over there. Documents. I'll call the sine example and we'll replace it. And now README has a little bit of a better, thing that shows a little bit of error. Any questions? Not yet. All right. Close. So let's do let's implement the second order. So we have a center derivative. Let's do second order derivative. So, or we can always do center derivative of a center derivative, right? That could also work. And that will actually definitely work. So, but we can also just implement it right away without having to do it. So we also need the function and the step size that we want to estimate with. And in this case, we're going to do d2 of u, also a function lambda of x, and we use the other formula for u. So we go back here, we're going to use not the center one, but This is a good example. Let's use this one. So parentheses u of x minus h minus 2 times u of x minus plus, sorry, u of x plus h, and this divided by h square. We can return d2u as an executive. So now we can also use it to compute the derivative. And that was very easy. I hope that was very clear. So now I want to move on. Now that we have these two things done, I want us to move on to the next topic. No, this doesn't make a line. Okay, the next topic. The next topic I want to explore is, boundary value problem. So why this is important is because I want to show you how to solve an actual physics problems, and in general, when you think of any problem, actually, you normally it is bounded by something, right? It is a string hanging from 2 points, or it is fluid inside a pool, and so all these things create restrictions on the domain that you want to explore. And so I think it's a good idea to start looking at boundary value problems. So in particular, this is a good example. We'll consider the first, an ordinary differential equation that has the domain is an interval a, b, and at the corner a and b of this interval, we're going to have some restriction on the temperature. So here's an example of the heat equation. So it says that the evolution in time of this function, the time derivative of ut, is proportional to some constant in time, but it's a function of x, of the function u of x. Sorry, of the derivative of u with respect to x, and then the derivative again. I don't know if you can see here, but it's a second order derivative, really. And then plus some function psi, which is a source of heat. So if this guy is positive, it will be adding heat into the system at different points and at different times. And if it's not, it will be, or if it's negative, it will be sinking, heat away. This equation is the heat equation, but it's also sometimes called the diffusion equation. A lot of systems have this behavior where heat expands, it kind of distributes all over. There are other things that are also diffusive. For example, Brownian motion is also diffusive in the sense that you can have put a droplet of ink inside water, for example, and the way that droplet expands also follows a diffusion equation. Now, what's important is that these systems are not infinite, they're bounded, and so when you actually want to solve this equation, here's the heat equation again, written for the case where the material is homogeneous, so that coefficient k or kappa is constant. You just have the first derivative with respect to time of u is equal to k times the second derivative of u with respect to x, and then plus psi. This equation kind of requires you to know how do you start, like what is the distribution of heat at the beginning of time, and what are the temperatures at the corners. So when you evaluate at the end of the interval a, what do you have over time, and when you evaluating at the end of the corner, at the other corner, sorry, at B, what temperature do you have? So this type of boundary conditions sometimes are called Dirichlet boundary conditions or Dirichlet boundary conditions, and they have some meanings, but we're going to skip that for a little bit since we want to go first to the steady state problem, and that's just for motivation. So for the steady state problem, what we want to do, the type of problems that we're going to tackle is we're going to look at the derivative of the function u equals some other function, for example. It's basically a specific example of the heat equation where the function is not dependent on time. So if for some, that's why it's called the steady state. If u is not dependent on time, then the time derivative of it is 0 because it's constant. The derivative of a constant is 0. So this equation kind of reduces to this equals to minus that, right, as it passes to the other side. So we're going to just simplify it and just tackle this problem. And this is a second order ODE. And from basic theory, we expect to need two boundary conditions to specify a unique solution. So how do we do a numerical solution to this? I know that there are many techniques to theoretically solve this function, but we don't need to. And I think the goal of these notes are for us to never feel bounded by the need for theoretical solutions, and instead we can just go and program it real quick and get a plot of the behavior of the function right away. I think that is the goal, I think. And so if I give you some function f, you can very quickly maybe just boom, 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 write a quick script and it will give you the function u. And so let's do that. And so let's go to the next part. So simple difference method, simple finite difference method for second order ordinary differential equation, or we're going to call this ODEs. So, and the problem that we're going to tackle, so the problem looks like this, and we're just going to write it. So it's u prime of x equals some function of x, so we're going to say this is for x in some interval. So a less or equal than x less or equal than b. What's happening here? And then with some given boundary conditions, and those are, that u at a is equal to alpha, and u at b is equal to beta. And I think that makes sense. So, okay. So how do we tackle this? Well, we know how to approximate the left-hand side of u prime, right? So we have the discrete version. So the discrete version looks like, so actually let me just add here using the formulas that we wrote above, right, that we derived above. The discrete version of this problem looks like this, right? So okay, so and we can see it here on the node. So it looks like D2, right? D2 of some function. Of U is equal to F of X. So, and this is where it becomes interesting. So we need to choose a step size, remember? So this D2 actually has implicit here, there's an H, right? So there's in here, there's an equality that goes, I don't know if you guys remember, 1 over H square, right? Times U of X plus, what is the definition again? Here, yeah, U of X minus H minus 2U of X, etc., etc., etc. So I'm not gonna write it, but I'm gonna kind of keep that in mind. So in a sense, we need so notice that we need a step size H in order to discretize. This is basically the basis of discrete. Instead of having a continuous of points, we're gonna have points separated by H. The equation. So this leads for us to split the domain, right, which was the interval a comma b, into chunks of size h. So those chunks look like, for example, a plus h, a plus 2h, and then we have all the way to b minus h, comma b. So now I'll put some diagrams here to make it a little bit easier to follow. So, okay, so now we have a set of points. So yeah, so the domain, the chunks of size set. So this is a series of points. This is a series of points. That we're gonna call x of i's, for example. And the book calls it x of j. So let's do that. For j equals 1 all the way to some number m, right? So depending on the size of h, we'll get these numbers. Now, okay, so now we have this partition of the domain. We also have, therefore, our discretization actually looks a little bit like this. So this one is easier actually. Discretization of our function f looks like this, right? So it looks like f of x of j, right? This is the evaluation of the function at these points. And we're gonna call those guys, we're gonna call them f of j's, just for simplicity of notation. Maybe I'll put it in parentheses so that it's not so mysterious. We're gonna call all these numbers f sub j's. On the left-hand side, our second derivative is going to be described, right, at every point x of j in terms of its neighbors, because that's the formula for the second derivative, the discrete second derivative, right? So let's write that here. So d 2 of u of x of j. How does that look like? If you remember, so it was 1 over h squared. So 1 over h squared, and then we go u of x of j plus h, sorry, minus h, yeah, and then minus 2u of x of j, and then plus u of x of j plus h. Now, let's close this parenthesis. Okay, this is good. But let's continue. Let's continue a bit more, because what do we have here? And maybe I should expand this. Oh no, this, okay. Just so make it a little bit easier to follow the notation. Okay, well, you can see it in these notes here. What you can see here is that we're gonna call u of x of j. You can see here is that u of x of j minus h, it is precisely the point previous to x of j, right? So if x of j was, something, x of j minus h is actually x of j minus 1. So we're going to replace that. So we get u of x of j minus 1. So we're going like in a previous step, minus 2u of x of j, that remains, and plus u of x of j plus h, which it becomes x of j plus 1. So we'll do that. And that's where this comes to be. Now, let's do, again, just like we did with the f's, let's call them, let's call u of x of j, let's call it as maybe, and the way they do in the book is they call it u capital j, like this. And so now u capital j is the evaluation of the function at the point u sub j. And if you remember, this function is unknown for this problem. So the capital U sub j's are unknown. And so, but therefore, our equation, our differential equation now is no longer a differential equation, but it's an algebraic equation that looks like this. So it looks like, kind of like what is written here, that 1 over h squared of uj minus 2uj plus uj plus 1 equal f of xj. So I'm going to write that down. So u sub j minus 1 minus 2 u sub j plus u sub j plus 1, is equal to f sub j. And this is true for every j equals 1, no, 2, all the way to m. And why 2, sorry, for j equal 1, okay, so j equal 1 to all the way to n. Now, what is important here is that we notice that the values that involved here, let's say, for example, when we use, let's do it for j equal 1. What happens, example, j equal 1. What is happening at j equal 1? So at j equal 1, the equation looks, this is the same, the 1 over h squared. But when you think of u sub, and then j, remember j is 1, so 1 minus 1 is 0. And then 2 u sub 1, and then plus u sub 2, right? And this is equal to f sub 1. What's happening with, what is u sub 0? Now u sub 0, already here, u sub 0 is equal to little u of a, right? Because u sub 0 is x of 0, and this is u of a, and the boundary condition tells us that u sub a is equals to alpha. So that's super important. This is where the boundary conditions come into be. And the same thing happened and for and for j equals m, you get, for example, that u sub m plus 1 is equal to u, little u of x of m plus 1, and that is equal to beta, right? So what this is telling us is that the partition of the points x that we have done in the interval a to b, the first element, the x of 0, is a, and so therefore u of x of 0 is alpha, and the last point, m plus 1, so x of m plus 1, u of x of m plus 1 is beta. And I'll make a quick drawing just to make it easy later on. But yeah, so now we have, if you notice, we have for every j, so for every j, for every little j, we have an algebraic equation, of three variables. Right? This case is u sub j minus 1, u sub j, and u sub j plus 1. So you can see that, if this is true for every j, the equations kind of interlap with each other, right? So we have the equation before, for example, for j equals 1, the first equation, it involves u0, u1, and u2. For j equals 2, it involves u1, u2, and u3, and so there's the overlap of u1 and u2. Now for the next one, right, there's an overlap of u2 and u3. For the next one, it's going to be u3 and u4, and for the next one, it's going to be u5 and u6, and so on, all the way towards the very tail end. And so you can decompose that as a system of m equations, right? Because for every j you have an equation, and m unknowns, which is the evaluation of u at the endpoints. And you can write this system as a system of equations using this matrix here, and I'm going to maybe copy paste this because it might be a little bit too long to write down. I'm just gonna put it here. Yeah, and we saved it. Very good. And then I'm going to explain kind of a little bit vaguely as to how do we solve this system. So, so this creates a system of equations of the form, and I'm going to write it here, A U equals F, where A and F are given by what you see here. So actually, maybe it would be good to explain over here, right? What is happening here at the first and the last row of this, but it's following that the boundary conditions are alpha and beta. So from this equation, right? You can. I'm gonna just go ahead and record here. Therefore, what happens? So we're gonna move the u0, which we know what it is, which is alpha. We're gonna move it to the other side. So we're gonna have the -2. Maybe I'm gonna move this over here. So -2 u sub 1 plus u sub 2 is equal to f sub 1 times h, because we pass an h squared, and then minus, and this is interesting, u sub 0, which we said was alpha, right? And the other equation that we want to also highlight is towards the end, right, where we evaluate in j equals m. So we have u sub m minus 1 minus 2u sub m basically a function from NumPy called NumPy linear algebra solver. So it's a very good function. So I'm gonna add a note in Python, or let's call Python / NumPy or SciPy. These are the scientific computation libraries that Python has. One can use the linear algebra solve function to get u. So it kind of goes like this. As np, and then you get np.linalg solve a, b, and that returns your vector u. So you first have to define your a's, and you define b, which in this case is f, right? And you solve u as a linear solution of this and this. So yeah, that's how you do it. So how about we do an experiment, maybe based on the book examples, and then we can do it. We can ramp up the stream. So I think are there any examples here? Obviously there are lots of theoretical questions that you have to answer, like stability, like when the approximation is good, but I think we won't have time to cover it here, but it will be interesting to do in a further stream. Okay, in the meantime, let's just do some simulation. I think I can find a really good example, so let's just try it ourselves. So how about we test the second part where we sort of solve the steady state heat equation, and our forcing function f is going to be lambda x. What could it be? Maybe let's say a forcing function is x squared. I don't know how that would look like. And then we're gonna have a step. So h, just like before, that's gonna be maybe 0.2, and our domain a is gonna be 0, b is gonna be maybe 1, and we basically have to discretize our equation, right? So our equation, if you guys remember, it looks like u x derivative, right, equals to f, and so what that led was, I'm just gonna write the equation here. So 1 over h squared times capital U sub j minus 1 minus 2 u capital uj, and then plus u sub j plus 1, and then this is equal to f sub j. So we need to define the matrix A, and the matrix A is going to be, you can start to see, right? So kind of like how we had written before. And so maybe let's start with the vector u. So u is a vector, and we don't really know its value, so let's initialize it with oh sorry, actually we should, let's go part by part. So this is the equation. Remember that the first thing that we do is we partition the domain, right? So x, let's call it actually x. Yeah, I have. Hi Atomy, welcome to the stream. Yeah, I have. Have you been here for a while? I don't know if you can hear me okay. It's not so different. It's not so different than the heat equation, right? In a sense, you just have to add one more time derivative on the time side, which makes it a little bit more complicated, because in an elliptic equation you have basically two variables instead. So instead of having just x, you have it's a two-domain system, right? So it's a two-dimensional system. So you have x and t. Yeah, thank you for the comment. Yeah, I always wanted to teach, mathematics or physics, and I'm a little bit motivated to show, I guess, a simplified version of what sometimes is very hard, and I'm trying to do it for, I think, quantum mechanics, which normally is kind of scary and requires a lot of, I would say, advanced mathematics to show some interesting results, like quantum tunneling, for example. And I think you don't really need it if you are able to do some numerical computation. And so this what I'm trying to do today is I'm trying to write notes on numerical computation that are very easy, straightforward, just to get into it, and then you can apply them to quantum mechanics to get good, I think, interesting applications, but with easy or with no very deep mathematics. But yeah, thank you. Please feel free to ask more questions. Regarding your questions about elliptic free boundary problems, wait, I have worked with elliptic free boundary problems. Wait, that's very specific. That's my thesis, maybe. Who are you, Itomi? But actually, sorry, let me correct myself. I thought you were just talking about elliptic problems, but you went actually hardcore and you went elliptic free boundary problems. So that's, yeah, I guess that's more advanced, I would say, but that's okay. That's totally fine. Cool. All right. Let me see. I'm gonna follow you, Tommy. Okay, so that I can see what else you're up to. If you're ever on on Twitch. Anyways, what was I doing? Let's finish here this the system. So first, let's make a partition of the domain. So we'll go from A to B. Maybe we'll do 100 points, for example. This means that our step size is gonna be I guess it will do is maybe what I wrote before will not work, but so we'll do 100 points. Now I realize I don't know how to go back to the chat without there. Okay. I'm a grad student in pure math. Where are you a grad student in? In what university? This is basically that topic. Free boundary problems was one of my thesis topic and my own graduate studies. Okay, so we partition the point. Let's compute this vector f, which is going to be basically the function lambda, the f that we computed, evaluated on our vector x, and then we need to define the matrix A. So these are define the matrix A. And so if you guys remember, let's go back to the definition of the matrix A, and it's actually very simple. So we're going to try to create it for this arbitrary size that we're choosing. There's 100, right? So let's just quickly go back here. Yeah. Okay, so sorry. This is very interesting. Let me go back to the matrix A. Okay, here it is. But yeah, so it told me. So I'm from Brazil, but I'm spending some time in Princeton. Oh, cool. Okay, so yeah. So right, totally understood. So in free boundary problems, the domain depends on the solution. For instance, right, the derivative of u, or I guess that's Laplacian of u, is equal to up times chi. Okay, some function, right, and chi is the domain, right? It's a 1 in the domain where u is greater than 0, right? So in some omega, that totally makes sense. So if the function becomes negative, for example, it then becomes outside the domain. So the shape of the domain is changing over time. Yeah. I am super familiar. It's been a long time since I did that, but I worked on my thesis on the Stefan problem, which is a phase transition problem between ice and water, for example, right? And you solve the temperature in two-dimensional into D, and your domain is changing as the water is like phase transitioning, right? If the water is above 0 degrees, is ice, and if it's below 0 degrees, is water. Sorry, the other way around. And so as your temperature, for example, starts to diffuse, then either it melts, the ice melts a little bit more, and so it shrinks or changes shape, or the other way around. Like if the water is colder for some reason, then the ice starts to expand, right? So your domain changes over time. And I studied that. I proved a couple of things in kind of local well-postedness for that problem, and global stability, I think, in the same way. But there's definitely much more advanced than what we're trying to do here. I think I'm trying to do a much more simple numerical approach. I do kind of regret not ever trying some computational methods for a free boundary problem. I feel like it's very well suited for it. But at the same time, you have to prove that your numerical method is an accurate description of the system that you're modeling, and so that's tricky as well. But it's very cool. Yeah. Hey Tommy, please DM me on Twitter if you want to, or you can send me an email at what is a good one? Yeah, I think Gustavo at UCDavis.edu still works. Sorry, G Navarro probably. G Navarro at UCDavis.edu. But yeah, thank you for sharing. So yeah, anyways, let's define this matrix A. So A is gonna be an array, right? And we can have to define it in terms of the coefficients that we have here. And so what is the size of this array? So maybe we'll put some zeros, and we have to put the dimensions of these zeros, right? So what are the dimensions of this matrix? So this size is going to be 100. We have 100 equations, right? By 100, and you can say that we're going to iterate through it. So for I in range 100, and for J in range 100. Basically, we're going to go through each element of the matrix, and we're going to fill it in, right? So if first we know that in the diagonal there are -2's, so we're going to go if I is equal to J, we're going to say A sub I comma J is equal to -2. We're also going to say that what else we know? If J, so if J is equal to I -1, right? So if we are in row I and we are in column I -1, so one to the left, but also we have to make sure that this is not, so and J is not equal to 0, right? Sorry, maybe positive is a positive, right? You don't want to, wait, sorry, what would J be? So JB will go from 0, will go 0 will be 1. So what is I -1? So actually, okay, sorry, I see what I mean. So if I -1 is greater or equal than 0 and J is equal to I -1, then you want to say that A I comma J is equal to 1, and then finally if and actually you can do it on the same one, and if J in this case I +1 is less or equal than 100, and J is equal to I +1, then we're at the very bottom, and then this is A is of I comma J, and I'm being very inefficient with this, but it doesn't matter, is equal to 1, right? So this will populate your matrix A. And yeah, and Tommy, for sure I will contact you. Thank you a lot. So, oh, thank you. Yeah, definitely. You can go to my website and you can see my paper, I suppose. If you maybe I'll put it on the chat. My thesis has some papers out there, and where can I find it? Here. I worked on this paper with my advisor and a postdoc from King's College, so maybe I'll post it here. but it's dense. I mean, maybe it will be useful. I hope it helps. So let's give this guy a shot. So how about we print this matrix A just to make sure that it's working. Maybe let's run it just to see what we can do. Okay, the matrix looks correct. I think the only thing that I think it does not look correct. I think it replaced some stuff. So we want to get basically the -2s on the diagonal and the 1s on the other side. So maybe we have to do. So okay, so if I is equal to j, okay, maybe we have to do elifs. Elif and then elif. Okay, and then the rest should stay at 0. Let's try again. Okay, so now we see the matrix looks a little bit better. So -2s on the diagonal, yes, but then these 2s are not working. So 1, 1, 1. Also here is wrong. And then equals j plus 1. They have to be together. So we are not in the end, but we are the next one. I'm not sure if this is the problem. I'll obviously figure this out before I send my notes and the code to GitHub, but let's keep trying. Okay, now it worked. Okay, yeah, perfect. So you see the 1s are only in the diagonal. It was just a matter of this being silly. Okay, so now we have this matrix A, and so we don't need this anymore. And now we are going to just solve the system by using NumPy. So we're going to say, okay, so U, the solution, is NumPy and then linog dot solve, and you can just literally put A and an F, which we define over here, and this should give us the U solution. And actually we're gonna go ahead and try to plot it right away. So plt dot plot. I'm gonna put our discretize points and our solution U. And perhaps I'm gonna say I'm also going to put the forcing function just to see the effect that it has. So this is solution, and then plt.plots x comma f, and I'm going to say this is label. This is the forcing function, and then plt.legend and plt.show. Let's take a look. Okay, this was very easy to compute, and the forcing function, I don't know if it was very little. Oh yeah, it was kind of incomparable size-wise to the solution. So I'm gonna try to show it to you by maybe screenshotting this and pasting it on the. Oh, Albi has joined the stream, and I'm gonna put it here. And you can then see this guy as we got the solution for the forcing function. This is we said it was x squared. So actually, if you zoom in into this result, oh, actually maybe you need to see it like this. There. There. So the solution is here, and the forcing function is here. And I think what I want to emphasize more than anything is that we solved a differential equation in literally, you know, I don't know what it is, 10 lines. Maybe we plotted it, you know, and that took a little bit of time. But we didn't have to do any kind of intricate method for solving algebraic or differential equations. We didn't have to do any theory. Excuse me, monster, I'm streaming. And I think that's the key. So that's it. Maybe since it's already a little bit late here, I'll stop the stream. But thank you very much for joining. I'm getting some interesting thing, but it told me to thank you very much for joining. I hope it was interesting. Please contact me. I'll be very happy to talk more and share more research. And if you're interested in this type of course or more of this material, I'll probably stream again next week, probably the same day, same time, 8:30 PST, and I will post it on my YouTube channel, which I will link on Twitch. And I will also I also have a course that is coming out that is going to be basically a summary of these notes and a course on quantum mechanics for engineers, if that's something that is interesting to you as well, just to understand, to get the basic results of quantum mechanics, again using some numerical approach instead of the classic advanced mathematical approach. Alright, but that should be it. Thank you very much. Thank you very much all. I'm signing off. See you. I'll stop recording.